Hello, my name's Roger Watson and welcome to this session on choosing the correct sample size. First of all, a question. Why is sample size important? Well, there are several answers to that question, one of which is that we usually cannot access the whole population. And in fact, we usually don't need to access the whole population. In survey research, we need samples to be representative of the population, and in experimental research, for example in clinical trials, we need samples to be large enough to show real effects where inferential statistics are being used to analyse the data. First of all, let's take a look at surveys. How many people should a questionnaire be sent to is the usual question we're asking in a survey. The answer to that is enough to make the results representative of the population, no more than is necessary to achieve the above, because that wastes resources, and the sample size will be related to the size of the population. In an excellent book on survey research by Jackson and Furnham, they give this table relating population size to sample size. If you look on the left, you'll see sample size running from under 200 to 100,000, and on the right, the sample that's required. For populations under 200, we generally sample the whole population, and then it gives you the numbers for 500, 1,000, 2,000 and so on. And the thing that you should notice is that these are not linearly related. So if you've got a massive population like 100,000 to sample from, you don't need to take the same proportion of those. In fact, all you need is around 400. And this comes from working out the 95% confidence with 5% margin of error level for sampling from that population. And what I want to do in the next couple of slides is look at what the confidence means and what the margin of error means. You don't really need to know this because we tend generally to use that level of confidence and margin of error, and as I'll show you, there are online programs that can help you to work it out, but just so that you have some idea of what we're talking about here. First of all, let's take a look at the concept of confidence. Now, these are not easy concepts to grasp. The confidence level is the amount of uncertainty you can tolerate. In other words, we are aiming to be 95% confident, but we tolerate 5% lack of confidence, as it were, in the answers to the questions. The only way we know what the true answer is to all of the questions is if we exhaustively sample from the population, or indeed take the whole population. So, for example, in 20 yes-no questions, we can tolerate in one of those questions, in any one of those questions, we're not specifying a particular question, we can tolerate a margin of error that's greater than the error that we set. The point behind this is that if you want to have higher confidence levels, you require much larger sample sizes. Now let's compare that with the margin of error, which is also not that easy to understand, but the margin of error is simply the amount of error that you can tolerate in the questionnaire. If all of your respondents were answering 90% yes and 10% no to questions, then you would have a very low margin of error, because you would be almost certain which way people were going to answer the questions. However, where questions are split very closely, you will have error creeping into the questionnaire. And again, you won't know what the true answers are unless you sample the whole population. So we tolerate 5% level of error. And again, the point here is that if you want to have lower margins of error, you require much larger sample sizes. So I think what you need to take from this is that conventionally we use 95% confidence with 5% margin of error. And as I said, there are online programs available, free, which help you to work out sample size, and RowSoft is one of these. This program allows you to put in the margin of error, the confidence and the population, and it tells you by using an algorithm how many people you need to sample. You can find this online at rowsoft.com. Next, let's just take a brief look at the relationship between populations and samples. Population is all the members of a particular group. A sample is a subset of the population. A representative sample is a sample that is like the population, and a biased sample is a sample that's unlike the population. And the sampling error is the difference between the two above, between the representative sample and the biased sample. So how do biased samples arise, and what's the problem with them? Well, they arise from poor sampling, and they may result from poor response rates. For example, only middle-class educated and motivated people may respond to a survey. That immediately gives you a bias. So to address this, we use different sampling methods. Sampling methods are described as being probability or non-probability. Probability sampling tends to give you more representative samples, and the simplest way of doing this is simple random sampling from the whole population. Everyone has a number assigned to them, then you randomly look for those numbers in the population using some sort of random number generator. We can also use stratified random sampling, whereby we randomly sample from different groups to make sure that those groups are represented. For example, some groups may be small and some may be large. If, for example, you were looking at a hospital, the management group would be small and the group of staff nurses would be big, so you'd need to sample differently from those. It depends what you want to get out of your survey. There are other more complex random designs like block randomization and so forth. This is not the place to go into these in detail. Non-probability sampling, there's nothing wrong with it because sometimes you may only be able to do it. The point is that you have to declare it. You can use opportunistic sampling, just taking people as they come along, or systematic sampling, taking every second, third or fourth person, for example, or purposive sampling, whereby we look for people with particular characteristics. And of course this is very commonly used in qualitative research. So what about sample size? Well, sample size also depends on the statistical tests that you're going to use. And this is determined by means of power analysis. And there's a classic paper by Jacob Cohen from 1992 called A Power Primer in the Psychological Bulletin. This paper is well worth reading. Not only does it explain the concept of power and the effect size, which I'm going to come to, it also gives you a table, which is a handy algorithm for choosing sample sizes for different tests. Power analysis and sample size is related to the effect size. So we'll look next at what an effect size means. To explain effect size, I really can't think of a better way of doing it than it was done in Wikipedia, as I've shown here. In statistics, an effect size is a quantitative measure of the strength of a phenomenon, and examples of these are correlation between two variables or regression coefficient, the mean difference between two means, for example a treatment and a control, or even the risk, any measure of the relationship between two variables. And for every type of effect size, whatever type it is, the larger the value, this indicates a stronger effect. And effect sizes are crucial for power analysis, and they're also crucial for studies such as meta-analysis. Now, Cohen from the previous paper suggested that an effect size of 0.2 be considered small, 0.5 medium and 0.8 a large effect size. This was just a way of helping him to indicate how to choose statistical tests. And this is how to calculate an effect size. The effect size D is the mean of group 1 minus the mean of group 2 over their pooled standard deviation, and the equation for working out the pooled standard deviation is given there. It's the sum of the two standard deviations divided by 2, and the square root of that is taken. So that's the formula if you ever happen to want to work out an effect size for the difference between two means, which is what we most commonly want to do for clinical trials and experiments. However, we don't have to think about that too much, because Cohen, as I said, produced some useful tables which I'm going to show you next. And here's Cohen's tables, or table 2 from his paper. So this gives you a range of p-values, 0.1, 0.5 and 0.1, and it also works out the effect size for a power of 0.8, which is the conventional power that we use, and it shows a range of effect sizes, small, medium and large. So for example, if we wanted to look at the difference in means between two groups, we'd look at line 1, which is mean difference. If we set alpha, or p, at 0.05, and we were assuming a medium effect size, we see from the tables that we need 64 people in each group. So in fact you need 128 people altogether. Now, a word of warning about sample size. If we had a sample of 100 people and we divided them into men and women, and there were 50 of these, then young and old, 25 of those, and then those who were well and those who were sick, you see that the numbers get very small. So you have to bear this in mind when you're sampling. So if, for example, you wanted younger women who were sick, then there are 12 of them in a sample of 100. If your power analysis indicated that you needed 100 of those, you'd have to sample from 10 times the population, or 10 times the original sample. You'd have to sample not from 100, but from 1,000 people. So you do have to be aware that the more finely grained you want to make your analysis, or to specify the particular kind of person that you want in your study, the larger the sample you're going to have to take. Thank you very much for listening. This is my email. You can ask me any questions or make comments, and you can also follow me on Twitter. Once again, thank you very much.